Okay, I'm back here in Chapter 1, and we've talked about a number of the elements basic elements in a fiber optic transmission system, including the transmitter, the optical channel itself, which is the fiber, and now we're going to look at the receiver. And I've got two slides here on the receiver, one on detectors and one on receiver electronics, to give you the introduction. And so, starting with the detectors, that's an important part of the receiver. It takes as input light and as output a photocurrent. So, a detector uses the photoelectric effect. When photons arrive on the surface of the photodetector, a photocurrent is produced. And we're going to denote the photocurrent as I sub D, sort of the current from the detector. And we're going to say that it's directly proportional with a constant rho to the optical power input to the detector. And so this is the photocurrent ID, has units of amps. This rho constant is the detector, at least in the basic model, the detector responsivity, and it should be constant and has units of amps per watt. And finally, this is the incident P optical, incident optical power, and it has units of watts. Okay, so that's the basic equation which shows how our detectors are going to work. Now, responsivity does depend on lambda, often quite strongly. And so when we're looking at desirable properties for a photodetector, we're looking for, first and foremost, large responsivity at the wavelength in use. So we'll have different detector materials for different wavelength ranges. So detector, so this photoelectric effect is materials dependent, and we have silicon, very cheap, and it's good over the range from 300 to 1100 nanometers. We have germanium, which is good from 500 to 1800 nanometers. So that the silicon doesn't get us all the way up to the 1300 or the 1550 windows. Germanium does. It has some properties that we don't like in a receiver, and so we usually use indium gallium arsenide, InGaAs. And the InGaAs detectors have a range roughly from 1000 to 1700 nanometers, which is just perfect for us. It's more expensive than germanium, but has much better properties, in particular lower dark current. But these are the main materials, and we tend to use InGaAs as our material system for fiber optic communication systems. If you're working in the 850 window, though, go ahead and use a silicon detector. It's very cheap. So the responsivity is wavelength dependent through the material system, and you can actually draw a graph of the responsivity as a function of wavelength. It generally falls off below a certain wavelength based upon on the properties of the material, that is the work function. We won't go into too much detail here in Chapter 1, though. Other desirable properties are a low power consumption for your reverse bias, a long life, fast response, small size, and low cost. For the response, what we're interested in looking at is a curve, sort of a plot of the optical power input as a function of time, and then the response of the photocurrent also in time. And what we see is that at, say, at time, t naught, we see our optical power going from 0 to some value very suddenly, sort of an ideal step function input. But at that time, our detector our photocurrent does not instantaneously jump up to the value that it's going to level off at. And we can sort of take this time interval here and call that our response time, TR for response. Okay, so that's the response time of the detector, and we'll see that it's very important. If the response time is longer than the bit period we're trying to use in the system, then we're going to have big problems. So we'll see later on, all the way in chapter 12, that as we do system design, we have to consider not only pulse spreading parameter, but we have to consider the rise time of the detectors. We also have to consider, similarly, the rise time of our optical sources, and make sure those rise times are all less than, or in combination, less than a bit period for our signal. The detector is only one part of the receiver, though, and so we've got receiver electronics that we have to consider, and we'll just do a sort of an overview. So the photodetector is part of the receiver. We're abbreviating the receiver with the abbreviation RX for receiver. And the goal of the receiver is to create an exact reproduction of that original signal, the original information signal, binary voltage pulses that went into the transmitter. We want to get that same signal out. And so some of the most important elements of the receiver include the load resistor. So our photodetector produces a photocurrent here, and that photocurrent, we need to put that photocurrent through a load resistor to create a voltage, because we're interested ultimately in getting a voltage signal out. So we have to put that across some resistor to create some voltage signal. Associated with the load resistor is a circuit. We'll denote the load resistance RL. We may get a little bit into some of the details this semester on the load choice of load resistor. But for now, let's just realize that it's part of the receiving circuit. We also need to filter the signal. Our signal occupies some fixed bandwidth in the carrier. However, the noise that we're seeing at the receiver, due to a variety of factors, and we'll look at these in chapter 11, the noise is generally broadband. That is, it's white noise. It's covering all frequencies. And so if you detect all of that noise, you're detecting a lot more noise than you have to, because any noise which is out of the bandwidth of the signal could be filtered out. So what we do is we have a filter. We bandpass filter the signal only. To keep the signal and only the noise that's in the signal bandwidth. Okay, so all the noise that is in frequencies outside of that signal range we don't need, and we filter them out. And that helps increase the SNR at the receiver. So right, the SNR goes up. Okay. The other thing we've got to do at the receiver is figure out, whether we're looking at a 0 or a 1. And so the light is turning on and off, and so we're going to get some sort of an optical power as a function of time that goes up and down. Okay, and it's going to go up and down according to sort of the bit periods of the signal. So hopefully we're able to figure out when the bit periods are supposed to be occurring at uniform intervals of time. So I'll label this T, capital T sub B, the bit period. Hope you can read that, it got kind of small. And then our optical signal comes in, and maybe we have, maybe 0, 1, 0, 1, 0, 1, and we may have some noise here like this. And so maybe we can tell. So we're gonna take our decision circuit and we're gonna sample the pulses at this bit rate, hopefully right in the middle of each bit period, and hopefully we can tell a 0 from a 1. If we have too big of a noise spike, then we may have a problem. So what we'll do is we'll have some sort of a threshold power, and we'll say that any optical power above that value is a 1, and any below it is a 0. And you can see that I've sort of drawn the optical signal in red as kind of noisy. But you can see that if the noise gets too high, maybe we're going to cross that cutoff, okay, or the threshold value, and we'll have an errored bit. What we're interested in then is the signal-to-noise ratio. So we're going to sample the pulses, and we're going to try to determine a 0 from 1. And it turns out the bit error rate depends on the signal-to-noise ratio. And the signal-to-noise ratio is defined as S divided by N. Sometimes we use P for both powers, but I'm going to use S for signal power and N for noise power. And in general, if we plot, and I'm sorry, this is kind of getting small here, the bit error rate versus the signal-to-noise ratio on a log plot, what we're going to see is what's called a waterfall plot. We're going to see that as the SNR goes up, the bit error rate comes down. And so this is a waterfall plot. Okay, so you can take a low signal-to-noise ratio and get a high bit error rate, or we can take a higher signal-to-noise ratio and get a lower bit error rate. Okay. Okay, so that's the basic introduction to detectors in the receiver electronics. Thank you.